Okay, what we have here is exactly as the title implies, a block being pushed by a spring, and this is a frictionless situation. So this spring has been compressed some distance or displacement x from its natural length. We've placed a block in front of this spring, and when we release this system, the block is going to be pushed forward. And the whole goal here is we're trying to find the velocity of the block when it leaves the spring. That is how fast the block's going to be traveling this way when it's shot off of this spring. So, what I want to do is go through and use both force and energy to work out this problem and show you some of the pitfalls that are involved in this situation. So the first thing we're going to do is look at graphically what exactly is happening in this problem. So I want to look at the mechanical energy of this system. And when I say this system, I don't just mean the block here. What I'm actually talking about is the spring and the block. I want to look at the two things together as one unit, because that's everything that's going on in this problem, the spring and the block. Now we know mechanical energy is kinetic energy plus potential. Now in this case, we're not dealing with gravitational potential. This block, which has mass, is always at the same height. So gravitational potential energy never comes into play here. The potential we're worried about is actually elastic potential or spring potential. And so ultimately what's happening in this problem is we're starting with a spring that is compressed. Well, that means this spring has some energy initially stored in it, and that energy is going to be converted into kinetic energy. As this spring pushes the block forward, it's going to, of course, put a force on the block forward. Say this is the force by the spring, and of course this block is going to move to the right as a result of that net force, and so work will be done. So here we will have work done by the spring. Now because the force by the spring is in the same direction as the displacement, this is of course going to be positive work. Now before we start diving into things like the work energy theorem or dealing with kinetic energy, potential energy, anything like that, what I want to actually go through and do is look at not just the velocity but the acceleration of this block, because a big pitfall in this problem is people try to use kinematics and Newton's laws to solve this problem, and you flat out can't. And I'll show you why. So what I'm going to go through and do is work out the initial acceleration of the block, just to show you exactly what's happening here. So at any point with this block, and especially when we first let this go, there's a force by the spring to the right. So the sum of all forces on the block in the x-axis is simply going to be the force by the spring. And that is going to cause this block of some mass m to accelerate in the x-axis. There's nothing crazy here. We have no friction acting to the left, and this isn't on a hill or anything like that. So this is pretty simple and straightforward. Now we can easily enough expand this out, and we can say that the force by the spring is negative kx. That's going to equal mass times acceleration in the x-axis. And so we do a little bit of rearrangement here, and we find that the acceleration in the x-axis is going to be equal to negative kx over m. And this is an important result, not in solving for the velocity, but really in finding where people go wrong in this problem. And I'll explain why. When this block is first released, it's at some maximum displacement, which we're calling x, and so its acceleration is going to be given by this equation, which is all fine and grand. As the block moves forward though, the force by the spring is going to get smaller because the spring is relaxing. This is an ideal spring, and so the force by the spring is going to get smaller. As a result, this acceleration is going to get smaller. And the acceleration is not a function of time like we would deal with back in kinematics or dealing with motion and quantifying motion earlier in physics. All of a sudden this acceleration is a function of the position. And what people try to do here is either apply the kinematic equations to this problem to solve for the velocity, and that overlooks the fact that this acceleration is changing, or they make a almost as bad mistake, and that is they try to integrate this with respect to time to get to velocity, because they're all thinking back to earlier in the year and thinking, oh yeah, dv over dt is acceleration, so if I just integrate my acceleration, that'll give me velocity. Well, yeah, that's true when acceleration is a function of time. Here, acceleration is a function of position. So this is a no-no. You have to be careful with what you are now integrating with respect to. Kinematics were all based on time. Energy and work, these things are based on position. So you've got to be really careful with trying to create or apply old relationships that no longer are correct. So the way we're going to do this is using energy. And our best friend when dealing with energy is the work energy theorem. Now, if you haven't gone through and watched my video on where this comes from and how to use this, just click up here. It'll help you out, I promise. So what we're going to do with this is go through and simply apply this situation to this super useful equation. Now, we're going to have this block start at rest. And what that means for us is the initial kinetic energy is 0. The initial potential is all elastic. Like I said, there is no gravitational potential here, but we still do have potential we need to worry about. So our initial potential, just doing a substitution over here, is going to be 1/2 times kx squared. This is the energy stored in a spring. Our next term, our non-conservative work term, well, this would be force or work done by forces other than springs and gravity. And in this problem, we have no forces other than springs, gravity, and the normal force. And it's worth pointing out here, the normal force is straight up and gravity is straight down. Well, aside from the fact that these two cancel each other out, I hope you'll notice the normal force is at a right angle to the displacement, as is gravity. So neither of them are doing any work according to our equation for work, which was FD cosine theta. So our non-conservative work term, that's 0. Now once this block gets to this point right here, once the spring is completely relaxed, it's going to be moving at this velocity that we're worried about trying to find. So we're going to say our final kinetic energy is simply 1/2 mv squared. You can call this V or V final if you really want, whatever floats your boat. Call it V1, I dare you, double dare you even. Then our last term, our final potential. Well, once the spring is completely relaxed, it doesn't have any energy stored left in it. It will have given all of its elastic energy to the block, which will now be kinetic energy. So this final potential term, well, that's 0. So this actually works out really nice and really neat. Just subbing these two terms into our work energy theorem, we come up with 1/2 kx squared equals 1/2 mv final squared. And we're trying to solve for the final velocity of this block. So this is quite nice and convenient. I'm going to put VF over here because it'll drive me a little bit crazy if I don't. I'll actually leave this as VF squared just for the moment. So we've got this term. I'm going to go a little bit farther with this, just sort of to foretell what is coming in the future. VF is the square root of k over m times x. And this is the final velocity of this block. And this actually is going to be really, really, really important, not only in this problem, but when we get to something called simple harmonic motion for a block oscillating on a spring. This mathematically is going to be super important. So we'll be referencing this later, much later in the year, when we get into this darkness that is simple harmonic motion and start talking about differential equations, because the relationship between position and velocity is going to be so important. And that square root over k over m is super important as well. So this problem isn't too scary. This is the block being pushed by a spring. If you have a problem like this, just plug in your numbers. There's your solution. That's all for this problem, and that's all for now.